Assalamu alaikum guys, my name is Sajid and in this video we'll go through the A-level physics paper 5 of the Fastpapers mock championship 2026. Okay, so in the first question, this bit of information is given. It says a student is investigating the behavior of a capacitor resistor circuit as shown in figure 1.1. The circuit shown here, a neon lamp flashes on and off when it is connected across the capacitor with a potential difference Vf across the lamp is approximately 90 volts. The student has a number of unmarked resistors. It is suggested that the time period t of the flashes of the lamp is related to the resistance R of the resistor by the expression given over here, where C is the capacitance of the capacitor and K is a constant. The constant K is given by this equation right here, where Vi is the potential difference across the input, Vf is the potential difference required to make the lamp flash, and VL is a constant. Design a laboratory experiment to test the relationship between T and R. Explain how your results could be used to determine a value for K and VL. You should draw a diagram on page 3 showing the arrangement of your equipment in your account. You should also pay particular attention to the procedures, measurements taken, control of variables, analysis of the data, and safety and precautions. Right. Okay, so from the information provided, we can tell that T, or the time period of the flashes, is dependent on R, the resistance of the resistors. So our independent variable is going to be R, and the dependent variable is time period T. So if these two are the variables, the quantities that need to be kept constant would be C, the capacitance of the capacitor, and the input voltage of the supply. Okay, so the independent variable would be R, and the dependent variable would be T, and C and Vi will be kept constant. Okay, so there are two diagrams shown over here, diagram 1 and diagram 2. Diagram 1 is the setup to measure the resistance of the resistors, and diagram 2 is the setup for our entire experiment. Okay, so firstly, we need to take a suitable number of resistors with different values and measure the resistance of those resistors using this arrangement shown on the left in diagram 1. Then we simply need to place those known value of resistances that we measured using an ohm meter in the place of R on diagram 2. Now, if we place a resistor R over here and close the switch, it's going to create a potential difference across the lamp over here. And if this VF reaches a voltage above 90 volts, the neon lamp is going to start flashing, right? It's going to start flashing. Now, what we need to do is measure the time period of each of these flashes. That can be measured using a stopwatch. So if we count or if we measure the time taken for 10 of these flashes, we can divide that time by 10 to find the time period of a single flash. And the time period of a single flash will depend on the resistance of these resistors. Now the procedures are given over here. We need to repeat the measurement of time period for every one of these resistors. And after finding the time period for one resistor, we change the value of R and find the time period of the next. This way we repeat the values for as many resistors as we have, preferably 6 or more. Now, after obtaining values of time and resistance, we record all these data in a graph, in a table. This right here is an example of a table with the column headings. There's no need to input the values. It's better to give the units over here. So R will be measured in ohm, and the values of time will all be in seconds. Now, after finding the values of time, average time, and resistance R, we plot a graph with R on the x-axis and T on the y-axis. Now, this equation tells us that T is equal to a constant. The constant is K times C. Let's denote that using another letter. Let's say a constant M times the resistance R. This is very similar to the equation of a straight line, y equal to m times x plus c. Here, the value of c is 0, so y-intercept is going to be 0, and x is the variable r. So the gradient is going to be the product k times c. So first of all, if we plot a graph of r of t against r, we should get a straight line that passes through the origin, and the gradient of this line, gradient, should give us the value of k times c. So the value of k would be the gradient of a t to r graph over the value of capacitance. Okay, now gradient can be calculated from the graph, and C, capacitance, is a known quantity. Now if we place the value of K in the equation over here provided to us, we'll get something like this. K is equal to natural logarithm Vi minus VL minus VL over Vi minus Vf, right? Yeah. Okay. Now our purpose here is to find the value of Vf. If we rearrange this equation, we get something like this. E to the power of k is equal to, E is the exponential function here, Vi minus VL over Vi minus Vf. Now rearranging this equation, making Vf the subject, gives us the equation written over here, where VL is equal to Vi minus Vf times e to the power of k. All right. We are supposed to find the value of VL, not Vf. So, okay, the same. Rearranging this equation gives us the value of VL over here. Okay, so we've taken care of the procedures that need to be followed. We've also uh, talked about the measurements that need to be taken. We've said what variables need to be controlled. And we've also talked about how the data can be analyzed. The precaution that needs to be taken in every one of these experiments is opening the switch before changing the value of R. If we keep this switch closed for too long, it might overheat the circuit. And the value of Vi over here must be a value greater than 90 volts, because for the neon lamp to flash, we need the voltage or the potential difference across the neon lamp to be more than 90 volts. So we can take this DC input supply voltage as something greater than 90. We can go with 100 volts. Okay, that answers question number 1. Okay, on to question number 2. A student is investigating monochromatic light passing through a diffraction grating. A series of maxima are produced on the screen as shown in figure 2.1 over here. Student measures the distance s between the central maximum and the second order maximum on the screen. The experiment is repeated for different wavelengths of light. It is suggested that s and the wavelength lambda are related by the equation shown over here. D is the distance between the diffraction grating and the screen, and n is the number of lines per unit length of the diffraction grating. A graph is plotted of 1 over s square on the y-axis and 1 over lambda square on the x-axis. Determine expressions for the gradient and y-intercept. Okay, so first let us convert this equation to resemble a equation of a straight line. Equation of a straight line is given in the form y equal to m times a variable plus c, where m and c are both constants. Okay, so to resemble this in the format of the straight line equation, we need to first we need to isolate 1 over s square and 1 over lambda square. So if we reciprocal both sides of this equation, it gives us s square plus d square over s square is equal to 1 over 4n square lambda square. Now, if we separate the denominator of these two terms, it gives us s square divided by s square again, which simply leaves us with 1. So we can write that as 1 plus d square over s square. Now let's write it separately. Because our purpose is to isolate s square, we can write this as d square times 1 over s square is equal to 1 over 4n square times 1 over lambda square. Now we have 1 over lambda square and 1 over s square as two separate terms. Okay, now if we keep 1 over s square on one side of the equation and send everything else to the right side of the equation, it gives us 1 over 4n square times 1 over lambda square minus 1. If we bring d squared to the right side of the equation, we need to divide d square by both of these terms. So let's simply write d square over here and over here. Now this term right here, 1 over s square becomes y, and 1 over lambda square becomes x, which leaves us with the gradient here and the y-intercept here. So the value of gradient would be, or the expression of gradient would be 1 over 4n square d square, and y-intercept would be 1 over d squared. Values of lambda and s are given in figure 2.2. Values of lambda and s along with the uncertainty in s. We need to calculate the value of 1 over lambda square and 1 over s square. Along with that, we need to include the absolute uncertainty in the value of 1 over s square. Okay, so let's compute one value of 1 over lambda square over here. So if we consider the first value of lambda, that would be 1 over 4.3 square. But notice that there is a 10 to the power of minus 7 included in the unit. So we need to multiply this 4.3 times 10 to the power of minus 7 and then square that term, which gives us a very large value. The value would be 5.41 times 10 to the power of 12. Now, if we divide this value by 12, 10 to the power of 12, we get 5.41. Now, 10 to the power of 12 is already included in the unit of 1 over lambda square. So the value over here would simply be 5.41. So the general idea is to find the value of 1 over lambda square, which would be lambda, the values given on the first column, under the first column, times 10 to the power of minus 7, then divide this by 10 to the power of 12. The values would be, the values of 1 over s square is even more straightforward because s is given in meters. So the values would simply be, now to find the values of the absolute uncertainties, we can simply use the equation for uncertainty. Uh, the uncertainty in 1 over s square, okay, the value 1 over s square only depends on s. So the uncertainty would have an equation like this. The absolute uncertainty over the value will be equal to the absolute uncertainty in s over the value of s. So absolute uncertainty of 1 over s square would be delta s, or uncertainty of s, divided by s multiplied by 1 over s square if we bring this 1 over s squared term to the right side. Now, rearranging this equation gives us delta s over s cubed. If we compute that for all of these values of s, it gives us uncertainties of, plot a graph of 1 over s square against 1 over lambda square and include error bars for 1 over s square. Okay, so 1 by s square on the y-axis and 1 by lambda square on the x-axis. The scales are already given, which is good for us. Now, the first value of 1 over lambda square is 5.41, which would be around here. And the first value of 1 over s square is 2.60, which would be around, 2.60 is right over here, exactly here. And the error in the value is 0.17, plus minus 0.17. So the coordinate would be somewhere around here, yeah, this, and the uncertainty is 0.17. So since the y-axis is 1 over s square, the error bars are all going to be vertical. An error of 0.17 is about this long. Now, if we draw a straight line from here all the way down here, that gives us the first error bar of 0.17. Now, if we plot all of the data, they look something like this. So here are the plotted points, the error bars, and the line of best fit, and also the worst acceptable line drawn in blue. Okay. Oh, by the way, we need to label these lines. So the red line would be line of best fit. Let's write that as best fit line. And the blue line is the worst acceptable line. Worst. Let's write that in blue. Yeah. So worst acceptable line. Now, we need to find the gradient of the best fit line. To find the gradient, let's select 2 points from the line. This point right here, it aligns perfectly with one of the plots. The x-axis value here would be 5.3. 5.3. And the value on the y-axis would be 2.4, and 2.5. Okay, so we need to take another point from somewhere around the bottom of the line. Uh, let's select this point right here. It seems to align pretty well. The x-axis value here would be 2.6, 2.7, 2.8, and 2.85. 2.85. And the y-coordinate would be here, which is 1.1, 1.12. Right, so the two coordinates we've selected is 5.3 and what's that value here? 2.5. 5.3, 2.5, and the other coordinate is 2.85 and 1.12. So the gradient would be 0.563. Now, the x-axis was given in units of 10 to the power of 12 per meter square. So we need to multiply the x-axis, which is in the denominator, by 10 to the power of 12. This gives us a value of 0.563 times 10 to the power of minus 12, which is 5.63 times 10 to the power of minus 11. 5.63 times 10 to the power of minus 11. Okay, now we also need to include the absolute uncertainty in our answer. The absolute uncertainty can be found by calculating the the gradient of the worst acceptable line. So let's do the same for this. We need to take two coordinates. So let's take one over here. The value on the x-axis here is 5.25. And on the y-axis, 2.66. Let's write these two values down in the page above, 5.25 and 2.66. So 5.25 and 2.66. We need to find another coordinate from this blue line. Let's take this coordinate here. The x-coordinate here would be 2.65 and the y-coordinate is 1.02. 2.65 and 1.02. 2.65, 1.02. The denominator will be multiplied by 10 to the power of 12, which gives us 0.631 times 10 to the power of minus 12, which is the same as 6.31 times 10 to the power of minus 13. Oops, this right here, the value here would be 10 to the power of minus 13, not 10 to the power of minus 11. To find the uncertainty in the gradient, we need to find the difference between the gradient of the best fit line and the gradient of the worst acceptable line, which is 6.31 times 10 to the power of minus 13 minus 5.63 times 10 to the power of minus 13, which gives us 0.68 times 10 to the power of minus 13. So the uncertainty here can be written as 5.63 plus minus 0.68 times 10 to the power of minus 13. So the y-intercept cannot be measured or cannot be taken from the graph here because the y-axis does not start from 0. We need to use the equation of a straight line y equal to mx plus c. Now you already know one of the coordinates of the best fit line, 5.3 and 2.5. We can make use of any one of these two coordinates. So 2.5 will be equal to the gradient. The gradient has a value of 5.63 times the value on the x-axis, which is 5.3 times 10 to the power of 12 plus c. The value of y-intercept would be minus 0.484. Minus 0.484. Now we also need to find the uncertainty, absolute uncertainty of the y-intercept. To do that, we need to find the y-intercept of the worst acceptable line. So let's make use of one of these coordinates we already found here, 5.25 and 2.66. The gradient of the worst acceptable line was 6.31. 6.31 times 10 to the power of minus 13 times the value on the x-axis, which is 5.25. 5.25 times 10 to the power of 12 plus c. The value of c here would be minus 0.653. Now, the difference in the two values gives us 0.653 minus 0.484, which is 0.169. We can round that to two significant figures to make 0.17. Using your answers to A, C3, and C4, determine the values of D and N, include appropriate units. Okay, so we had two expressions here. 1 over 4n squared d squared was the gradient, and minus 1 over d squared was the y-intercept. So minus 1 over d squared would be minus 0.484. So the value of d would be which is 1.44. 1.44. And our gradient was 1 over 4n squared d squared. 1 over 4n squared. Okay, since we already found the value of d, we can plug that in here. 1.44 square is equal to the gradient. The value of gradient is 5.63. 5.63 times 10 to the power of minus 13. So the value of n would be 463,000. Okay, so d would be in meters and n would be number of lines per meter. So meter to the power minus 1. Now, determine the percentage uncertainty in n. Now, the percentage uncertainty of n would be half the percentage uncertainty in the gradient plus the percentage uncertainty in the value of c, the y-intercept. If we compute the uncertainties, it gives us half times the percentage uncertainty in gradient would be the uncertainty 0.68 over 5.63, plus 0.17 over 0.484, which is 23.6%. That concludes the paper. I wish you all good luck for your exams. Inshallah, all of you guys will do good.